Hello again, welcome back to my computer vision series. Today we are going to have first video about generative AI, and we'll start with a simple concept of neural style transfer. So it's quite an old technology by now. So we take one content image, like the random picture of a turtle here. We take a style image, like the painting Waves by Mark Webster, and then we combine them to have the turtle as if it was painted by Mark Webster himself. So this is the first GenAI video, hopefully out of many. It introduces some important concepts that we'll need later on. Other than that, it is quite a cool technology on its own. This is the plan for today. First, we are going to just overview what the method is. So how do we combine these images to get a new one? Then I go a bit deeper into explaining main concepts behind the method. So how exactly do we do gradient descent over pixel values? What is content loss and style loss? What is gram matrix and why we use it here? And then we'll look at some results. Let's start with method overview. So we take a pre-trained model, something that could be used for image classification, for example, ResNet 50, VDG19. Some of these models, some of you have seen as backbones for model transformers or object detectors. In here, we just use the model itself. And we take a single pair of images. So our content image, the turtle, and style image, the waves painting. So this is the key difference to other methods and tasks in computer vision in general. So we don't need the data set. We don't need to label anything. We don't need to train a model. We just take one pre-trained model and a single pair of images. And then we combine them to get a new image. That's it. And the goal here is to generate a new image to match style of one picture and content of another. So we have our content image, and we pass it through our backbone, in this case, VDG19. So it basically consists of a bunch of convolutions followed by max pooling operation with stride. So we start with a high resolution image with just 3 color channels, red, green, and blue. Then after a few convolutions and the max pooling operation, it gets downsampled to smaller resolution, but more channels. Then again and again, until we get the final representation of the image. So in actual VDG19, the final output will then be fed into a fully connected layer, and the output of that are just class probabilities for different classes. In here, we are just interested in this final downsampled version of the image itself. We do the same with style image. So we pass it through the same network, and then we initialize a generated image. So we start with just a copy of the content image itself. Then we have our loss that will be represented as a sum of content loss and style loss. So content loss is a measure of how close the content of this generated image is to the original image. And the style loss is the measure of how close the style of this generated image is to the style image provided. And then we'll run the optimization. But instead of updating model parameters, we will update the actual pixel values of the generated image. So we will morph it in some way to get a different image. So while we do that, since we have started for the generated image is just a copy of content image, then the content loss is going to be 0. So as we run the optimization, the content loss will necessarily increase because it was 0 before, it can't go any lower. But we will minimize style loss. So the idea is to minimize the combination of both of these so that we change the image, but it still looks close to the original, but with a different style. And right now, the generated image is just a copy. So let's see what will happen after a few iterations. So after just a few iterations, the pixel values have changed, the colors have changed drastically. It doesn't really look like anything. We get some weird red stuff here and so on. Then after a bit more iterations, we're definitely getting this blue vibe. and maybe more wavy texture, then even better. And you can see slight texture changes from slide to slide. And then it looks like this. So now it certainly looks like something Mark Webster could paint, but we can see that it gradually got there, and it still looks pretty close to the original image. So let's briefly discuss gradient descent over pixel values. So how exactly do we run optimization over input picture? So neural networks can be represented as just a computational graph. So we have parameter inputs, we have input data, we have computation nodes. So dense layer takes input data, parameters, and just performs multiplication. Convolutional layer does something a bit more complex, but it's still along the same lines. And finally, the final output of this whole process is the loss. So usually, to minimize the loss, we compute gradient with respect to parameters. And this gradient is computed by backpropagating through the entire network. And then knowing the gradient, we update the parameters to achieve a better version of the network that has lesser loss. However, we can see that the actual parameters and input data are quite symmetric here. So there is nothing stopping us from just computing the gradient of the loss with respect to input data. And in our case, input data pixel values are, again, just numbers. So there's nothing stopping us to compute partial derivative of the loss with respect to these numbers, the gradients, and then run the optimization update of these pixel values themselves. And this is how we change our generated picture. And here is the equation for dense layer. So the ith number in the output is equal to sum over jth element in the picture with the this cross element in the parameter matrix. So we can see that this is just the multiplying of one number by the other. So you can compute partial derivative with respect to this term or with respect to this term. So they are pretty much equivalent here. So there's nothing stopping us from doing this optimization on the input image. Now let's discuss content loss and style loss. So why exactly we get this feeling of wavy texture from the style image and then the content of the turtle from the content image. So what constitutes the content and the style? So first, content loss. How do we do that? So we have our content image, we have our generated image. We pass both of them through our VDG19 network. And then for content loss, we are only going to use the final layer output. So the final downsampled representation with low resolution, a lot of channels. And then we'll compare them by using just per pixel mean squared error. So for this pixel on the nose here, we're going to compare it to this pixel on the nose in the original image in the downsampled version of the image, and just compute mean squared error. So the actual difference, the square difference between the value of the pixel. And we'll do that and we average out for all the channels within this downsampled version. So one way to do that is to use mean squared error, the squared difference averaged over all pixels. Another one is to use binary cross entropy. So we've used cross entropy for classification before. That's when you have your one hot encoding vector, or in case of binary, that's just either it's turtle or not, for example. So it's 0 or 1. And then you have your predicted probability, which is a real number between 0 and 1. But you can also use binary cross entropy to compare two real numbers with possibly fractional parts if they are from 0 to 1. The math just works the same. So in here, binary cross entropy is pretty much the same as mean squared error. It's just the actual curve of the loss is a bit different. So really, the most important part of this entire neural transfer method is understanding how exactly convolutions work inside and how we can use that to get this neural style transfer effect. So I'm going to show you some pictures from a really important popular paper called Visualizing and Understanding Convolutional Networks. So basically what they did is they took a convolutional network and they tried to generate images such that this certain piece of the image will maximize a certain pixel in this downsampled version on every layer. So they do that by running deconvolutions or transposed convolutions. So they have the trained version of the network, they apply just some image to that, and get the activation value, so the value of this particular pixel in this feature map. And then they run the transposed convolution from that by basically taking the original path, by transposing it, by doing some stuff with unpooling to get up the upsampled version back. All of that is described in this paper. But basically what this achieves is some representation in the original pixel space that maximizes the activation value for this particular neuron, for this particular layer output for the pixel. So we can see that for the first layer, that's mainly just gradients or edges. And then for the second layer, we see some more interesting patterns like circles, maybe some grid patterns and so on. And to the right, we can see the patches from the original image that caused this activation. So just ridges, edges, circles. And then as we get further down the network, it gets progressively complex. So here we can see some cell patterns. This looks like a wheel. And this almost looks like a person. So by the third layer, we have individual filters, individual neurons that can recognize outline of a person, or in here it sort of looks like some text, and this is it in the original image. Then as we get even deeper, we start to see interesting stuff like dog faces, birds, and so on. So to sum up, the first layer of this convolutional network, it will mainly be responsible for processing raw pixel information and turning that into something like edges or texture. And then as we get deeper in the network, we get more complex, more abstract things represented in there. So we go from just ridges to edges to circles, then to grid patterns, and to entire numbers and letters and face outlines and birds and dog faces and so on. So deeper layers in the network are responsible for detecting more complex patterns in the picture. And so this is why when we compute content loss, we only connect the final representation. So it is going to look at, in this case, a turtle. So the final representation should have pretty good idea of what the turtle is, and minimizing that loss should force our generated image to still contain the turtle in the same place, because we have the convolution, so the actual location of this pixel matters as well. But we can change the look of this turtle. And then for style image, we use these earlier layers that represent less of the content of the image, but more of a texture of maybe the type of brush and stroke used to paint that, or just the overall color composition and so on. When we compute style loss, apart from only comparing the earlier layers within the model, we also use this Gram matrix that I will talk about a bit later. So Gram matrix represents some cross correlation between feature maps. So we first compute the Gram matrix of this layer and this layer and this layer in the generated image, and then Gram matrix for this layer, and this layer in the original style image, and then we do the comparison between these two. So we compute again per element mean square error, but instead of the picture or downsampled version of the picture, we look at this gram matrix. So here is another picture from the same visualization paper that sort of shows the same thing. So we can see that down below here we have, so they basically try to reconstruct the original image from the pixel values in the downsampled version. So from the first layers, you get pretty good reconstruction of the image itself, right? So if we zoom in here, it really looks like a house. As you go deeper, the reproduction ability decreases because the entire image is now smaller. So the downsampled version only has low resolution. So it actually has less information in it. But you can see that it still does a pretty good job in representation. So it's not getting all the edges, all the high resolution information precisely, but it still definitely looks like a house. So it got the main thing correct. So it basically says that here's a house, here's a roof, but it has lost this precise pixel information. And then for the style, we'll have the same thing. So the first layers will just represent like overall texture, maybe color composition. And then as we move deeper and deeper, we'll have this more complex patterns represented and the actual objects located in the image and so on. And here is the example of applying different styles to the same picture. One thing you notice here is that overall picture composition does look like the content image, right? So if you compare the Starry Night to the transferred version, precise locations of the stars and so on will be different, but the location of the house and the river will be still the same as in the original picture. So we get the geometry and overall positions of the objects and what objects there are from the content picture, and then the stroke and maybe texture, paint style, and then if we take higher up, and then if we take deeper levels from the style image as well, we get overall high level objects as well, but they might be located at different places. So now let's discuss the gram matrix, the thing that explains how exactly we transfer the style. So this is the equation for the gram matrix. So we basically have our x and y coordinates within the image, and then we have f1 coordinate and f2 coordinate that basically represents the index within the feature map. So for a layer down below, deep within the network, we might have 512 channel maps, feature maps. And so the gram matrix will, each element in the matrix will represent some sort of correlation between these two feature maps. So without even reading the formula, you can see that we've started with something that contains x and y coordinates, so the actual image, right? But then after summation, all of that is gone. So gram matrix itself only has only has numbers for either just feature map itself, like overall average of that, or cross correlation between two feature maps. So we don't have this x and y position in the gram matrix anymore, which means that gram matrix is not representing positions. Position has gone away out of the calculation. So we no longer care where exactly these patterns, these textures, and these objects are located, but we care about what is there. So for cross correlation between two feature maps, you basically take one picture version for the first feature map, one pixel image for the second feature map, and then you compute the dot product. So you compare two pixels and then just multiply the values, which shows that basically for diagonal elements, for the correlation between feature map and itself, you just basically say how many of these things there are. So if you got a feature map that represents stock heads, this cross correlation to itself will tell you how many dog's heads there are. And then if you have a pair of those, maybe dog heads and the letter A, So if you have a particular filter map that is responsible for detecting letter A, then this cross correlation will tell you how many dog heads with the letter A on top of them you would have in the picture. So, and that's obviously for the deeper levels. And then for shallower levels, you would have less complex patterns like just gradients or edges or corners and so on. And the actual loss is calculated as mean squared error between two gram matrices. So the gram matrix from the original image and the original style image, and the gram matrix for the generated image. So it no longer cares about positions. So it doesn't care where those dog heads with letters A on them are located, but it cares how many of them there are and if there are such objects in the picture. So now that we know all the details about loss and how everything is implemented, let's go over the entire algorithm one more time. So we start with a content image, picture of a turtle, and a style image, painting with waves in a certain style, and then initialize the generated image as just the copy of the content image. Then we have the content loss that cares less about specific details, specific pixel values, edges and strokes and colors, but cares more about the actual content of an image. So is it a head of a turtle? Is it a turtle at all? Is it sky? Is it sand? And it cares where it is located. So we need to have a turtle head at the same spot as in the original picture. And then we have the style loss that uses this gram matrix to get rid of positional information and uses earlier layers of the network as well as deeper layers. So we now care more about specific colors, pixel values, paint styles, texture, all of that details of the image itself, as well as higher level objects. But we no longer care where they are. So we just want to see some waves in there, some paintbrush strokes, and so on, but we don't care where. And we optimize the generated image. This is the same as training and changing the parameters of the network, but now instead of the parameters of the network, we change the picture itself. And so after a few iterations, we get a picture that still has roughly the same stuff in the same place as the content image, but with style and the paintbrush and the curves and waves applied from the style image. So I hope my explanation was clear enough and that it helped answer some questions. Now let's quickly go over results. So this is the picture we've seen already from the original paper, where they take a photo of a city with a river and houses and try to apply different styles to it. And we can see that really it works. So the color composition changes a lot in this case. The paint style, the strokes, the overall feel of it is indeed taken from the style image, while you still can see the original houses and river all in the same place. So this really works. And this is our example with the turtle. And again, you can see that the rough outline of the turtle is still the same. You still have the clouds in the background and the sand and the beach. But it is now in this style of bluish, wavy curves. Here's another one. So I've tried to take a selfie and just apply the same thing to it. And we can see here that my face is a mess. So it does care about just high-level composition, but it doesn't care so much about like all specific details that composite a face. And that might be a problem with just the network that we've used, that maybe just can detect a face, but not differ to faces between each other. And maybe it's just too crude. So the method itself, it doesn't care that much about creating this high resolution, precise image in the style. It just sort of crudely just morphs everything together on top of the original image. And so in this case, it just loses my face entirely. And now in 2024, we know that there are better techniques to do that with transformers, with proper image generation. So neural style transfer is pretty much outdated as a useful technology, but it's still cool, and it still helps introduce some useful concepts. So to sum up, this technique doesn't require any training, any dataset. So we just need 2 images, no labels, pre-trained network, and then we do this gradient descent to generate a new image. Because of that, it is really slow compared to just doing one step of model inference for one image. To get a generated image or to get a prediction, we now have to do all of these optimization steps, and it is just slow and resource consuming. So it's hard to imagine doing that like in real time on a mobile device. So it's not that good. At the same time, it is really crude. So by doing this merging of pictures in this way, we lose a lot of detail. We might lose a person's face completely. So it's not the best technology out there at the moment. And now a reminder. So in my channel, I try, apart from just doing cool videos explaining complicated concepts in easy terms, I also try to set out the learning path. So something that if you don't know where to start, you can just start at the very beginning. And then I introduce all the concepts gradually so that you can follow it, so that you can understand all the fundamentals and really get into it. So by now I have a lot of videos about image recognition and object detection. So we've started with just a simple solution using dense neural network that you can just sit down and code following the online tutorial in half an hour, and it doesn't use any advanced concepts. Then we threw in a lot of concepts like convolutions, activations, severe initialization, batch normalization, residuals, and so on and so forth, to really scale up our game, to be able to train models on big data sets with a lot of layers and still get good results. So the final step in that was reproducing the original ResNet 152 model, which was the winner of 2015 ImageNet competition to classify images. And we have actually trained such a model ourselves. We've looked thoroughly at the code. So as usual, real code that solves real problem is much more complex that you might get in other tutorials that just introduce concepts without showing how exactly everything sticks together. Then we moved on to object detection. That's when you might have several objects on the picture and you need to draw bounding boxes to actually say where every object is, apart from just classifying it. We've discussed YOLO to do that. We discussed Deter, which was maybe not a good model, but a good fundamental way to do object detection. Then we discussed an advancement of that called deformable Deter, and in the future videos we'll discuss other advancements like dynamic anchor boxes and denoising and codeter that allowed the quality to basically explode and become much better than we've seen even 2 years ago. And we finalized that with discussing the state-of-the-art model. At the same time, this video was the first one in the generative AI series. So it branches out from about here. So you don't need advanced transformer concepts to start understanding this, but you do need to understand what are convolutions and main techniques behind computer vision of that time. And so today we did neural style transfer. The very next video will be about implementing neural style transfer in code, so you can do it yourself. Then we'll move on to unconditional image generation. That's when you have a trained model, you tell it to generate an image, and it generates an image that usually looks something like the images in the training data set, but you can't really control what is there. So it's not really that practical. And then we'll start out on the long road towards text prompts. That's when you can write a prompt and have the model generate something that actually looks like what you've described. And that's going to be much harder. So see you there.